for a slip and slide, and here's Team Nitro.
Team Nitro!
But what science will our slider reveal? Did you guess the science this slippery speedster is about to demonstrate?
Team Nitro!
That's right, it's the coefficient of friction. A smooth plastic sheet covered in lubricating water has an extremely low coefficient of friction, and so he maintains his momentum and he hits 20 miles an hour. And then a table. Bit early for lunch, mate. Come back in 5. In 1947, Chuck Yeager flew at a top speed of 700 miles an hour and became the first person to go through the sound barrier. But he was a long way from being the first person to break the sound barrier. Whips date back longer than written records. And in the right hands, you can use them to break the sound barrier time and time again. Which I think calls for a harmonica solo. Oh yeah. Of course, in the wrong hands, they're just 6 feet of pain. Now, whip cracking is a dangerous hobby, and it's not one that I recommend unless you know your science. Our cowgirl flicks the whip's handle back and forth rapidly, creating a loop that passes energy along the whip's length. As the whip tapers, the energy travelling down it is conserved, but the mass of each section decreases. This means the velocity increases until the end of the whip is travelling faster than the speed of sound. So the loop tightens and breaks the sound barrier, producing a pressure wave that we hear as a small-scale sonic boom. The crack. This was all discovered by other animals well before humans. The 2-inch pistol shrimp snaps its claws to produce a similar cracking shockwave. But why start small? The longest whip ever cracked was nearly 330 feet long.
Oh, that scares the hell out of me.
This one is only 80 feet. But it still has a bit of a kick. The force of the pull overcomes the whip's friction with the ground, and it loops back towards him in quite a painful way.
Well, that is by far one of the stupidest things I've ever done in my life.
These two look a lot more professional. They've even got a routine, and it looks like they're building up to a big finale. They call that one the showstopper, for obvious reasons. As their whips taper, the wave added at the handle increases in velocity until the thin end is going faster than 770 miles an hour. Fast enough to snap the tip. So that is going to leave a mark.
Let's see how fast I get in trouble cracking this whip inside the house.
All right, settle down please, class. I hope you've all got your notepads at the ready, because it is time for today's science lesson, the part of the show where we focus our microscopes on one particular scientific principle. So, do you know what these 3 things have got in common? This reluctant ride, this swift stopping skater, and this reckless rally driver. Don't worry, they were fine, eventually. Okay, hands down everybody. Yes, they're all examples, of course, of acceleration. We're all probably thinking of the same thing when we say acceleration, a change in velocity over time. But do you know about negative acceleration? And what about centripetal acceleration? Well, prepare to be schooled. As this remote-controlled car speeds off, energy is supplied by the engine and it experiences positive acceleration. And as it brakes, it experiences negative acceleration, a velocity change in a negative direction. Since velocity incorporates both speed and direction, as the car turns, even at a constant speed, it's accelerating. This is called centripetal acceleration. And when it takes off from a jump, it's experiencing the constant gravitational acceleration that brings it back down to Earth. Right now, let's see who's been paying attention with a little pop quiz. Question 1. How is acceleration defined? That's right, it's a change of velocity over time. In this case, quite a lot of velocity in quite a short time. That was an example of a positive acceleration, but question 2 is, what does a negative acceleration look like? Like that. This time the bike negatively accelerates when it hits that ramp, and then he negatively accelerates when he hits the bike.
That was epic.
Question number 3. When is maintaining constant centripetal acceleration most important? That's right, on a corner. Speed remains constant, but in a more sideways direction. Like that. So that's acceleration. All right, class, dismissed.